is about leveraging SRv6 on P4 programmable switch fabric at network edge. Okay, so we have two speakers, Jesper Eriksson, who is VP Product Management at NoviFlow, and Daniel Bernier, who is Technical Director at Bell Canada. So first is Jesper. He's a VP of Product Management at NoviFlow and one of the co-founders of the company. At NoviFlow, he leads a team of product managers, sales engineers, and software engineers responsible for product management, sales engineering, and prototyping in collaboration with service provider. Prior to NoviFlow, Jesper worked at Ericsson and Nokia with mobile systems in various technology and commercial roles. Jesper holds a MSc from the Royal Institute of Technology and an MBA from University of Virginia. So welcome, Jesper.
Yep, thank you. So will you introduce Daniel later then? Or?
Daniel will speak?
Yeah.
Okay, so you have to hand over. They should be ready, I guess.
Yep.
Thanks a lot. You have a pointer?
Okay. Very good. Thank you, Bruno. And good afternoon to everyone. I'm very happy to be here on behalf of NoviFlow. And we're going to talk about a project that we started with Bell Canada in July 2019 and around SRv6. And Daniel is going to, I'm going to start with the first slides, and then Daniel will add some more technical depth and you know, how the operator was actually using it and benefiting from it. So there are really three components in this project. Bell, through Daniel Bernier, provide the technology, architecture, vision, and then NoviFlow, we provided the software for the solution. And then Lanner Electronics provided the hardware that we built the software on top. So, and it's really about using SRv6 and programmable networks to reduce service cost at the network edge. And this is the first time we ever talk about this publicly. So I'm very happy that we're able to do this. So the ambitions that Bell had going into this project was really build a network for the future and make it easier to deploy network services. And the other thing was to make it more simple and be able to move services to the edge. And the last part was to be able to scale these services, you know, either physical or virtual appliances. And we all played, you know, different roles, you know, I mentioned before in this project. So starting with NoviFlow, what we contributed was, at the core was our NoviFabric, which is an SRv6 enabled network fabric. And it does some very specific functionality that I'll get to later. And the ideal use case for this NoviFabric is at the network edge. And from an operating perspective, we're targeting the near edge, not the far edge. And this is where the operator will run their own network services before they hand off either to the edge cloud, you know, one of the public cloud providers, or you ramp off to the internet, or you send traffic further up into your network where you have more centralized network services. So the kind of services we talk about are various security services, user plane function, CGNAT, and the ability to break out into the clouds. This NoviFabric, of course, can also be deployed in other locations in the network. It can be even at the customer premise, the near edge, the edge CO, the local data center of the service provider, or even a centralized data center of the service provider. And the NoviFabric allows you to seamlessly move workloads between these locations. And we'll explain that a little more in detail. The hardware platform that we use for the Bell deployment is the Lanner HTCA 6600. So it's a white box with 2 Tofino switches running 1+1 active-active, and up to 6 compute blades, each with dual socket Intel processors. There's also storage built into the platform that could be used for some use cases. And then what NoviFlow brings, besides the Novi Edge, is management software managing the entire platform. The platform, a couple of more things about the platform. Comparing the Lanner HTCA 6600 to more traditional deployments, we see a significant reduction in CapEx cost, acquisition cost, footprint, and power. And of course, in the end also, by having an integrated platform, you don't have to worry about cabling between the servers and the load balancers and the switches. It's all done in the backplane. So what do we actually do in the NoviFabric? So we develop something we call an SRv6 service proxy. And it acts as an orchestrator, an enforcement point for service policy. So the operator decides, okay, I want traffic to go through these services as it traverses the network. What NoviFlow does is we provide the means to be able to insert one or more services in that flow through acting as an SRv6 service proxy. And these services are invoked in order. It's an ordered list of services that we execute when the packet arrives. And we support different service types, and I'll get to that later. And then the services can either be hardware or software-based. And within NoviFabric, we have a built-in load balancer, and the service chaining is also built in. And this is what's been in production since November last year at Bell. So here's a little more next level of detail on the NoviFabric. And it kind of shows an easy example of a host X trying to send a packet to a host Y on the right and traversing a mixed network with some SRv6 enabled routers. Other routers don't support it. And the ingress router, router A, classifies the packet, inserts a number of segments that it wants the packet traverse as it goes from X to Y. And one of those segments is the NoviFabric. And once the packet gets to the NoviFabric will interpret that segment and then execute a specific service policy. It could be a firewall, it could be a firewall and DDoS, it could be any number of services. I think up to 5 services that we can chain, and for each service we would load balance 2 or more individual resources. So the NoviFabric acts as a proxy for these services. They don't necessarily have to know They're part of an SRv6 network. We basically just serve them up a packet, they process it, and then we send the packet on to the next link in the service chain or the next hop. So what makes this interesting is those services now suddenly become addressable on the SRv6 network. And we have two implementations. One is the 128-bit SID, the full SID. But we also have a micro SID implementation. So this service chain, each service chain is its unique SID. And we actually created this SRv6 function called n.sc. And it, from an SRv6 perspective, it looks like a binding SID. But the interesting part is you separate the execution of the policy from the rest of the network. So imagine you have a security team defining what the policy entails, whereas what you advertise on the network is just a policy. I mentioned we support different service types. So when we looked at the different network services, we divided them into three categories. The first one, of course, is the network service is SR aware. It has its own SID. It will process the SRv6 or the SR header and step the pointers, etc. Unfortunately, there are very few services out there that are SRv6 aware today. You look at most security services, etc. They don't support type 1. So type 2 is the next possibility, and that's what we call an SR pass-through. The service does not process the SRv6 SRv6 information, but it's transparent. It treats it as a tunnel. It will actually process the packet that's encapsulated inside a SRv6 header. And once it's processed, it doesn't change anything in the SRv6 header. And then type 3 is, and this is the most difficult one to deal with, is if the service is SR unaware and will fail the execution. You feed the service an SRv6 packet, it will drop it. And type 3, to deal with type 3, you essentially have to remove the SRv6 information, serve the original packet, inner packet, and then when the packet comes back from the service, you recreate it. So what NoviFlow has built so far is a type 2 implementation and a type 3 implementation. So at this time, I'm going to hand over to Danielle to talk about the next few slides. Okay, over to you, Danielle. And I'll keep forward the slides. We can't hear you.
Yeah?
Once again?
Can you hear me now?
Yes.
Okay, so sorry about that. The marvels of being remote. Thank you very much, Jesper. So the first thing I wanted to talk about is the fact that once we started with the standard base SRv6 segment ID format, but we switched over during the flight of our journey towards UCID. And what we realized is there was both worked. Tefino actually could handle back from when we started the SRv6 journey with more than 10 SIDs, standard base. But with UCID, what we realized was we actually got better advantages. First of all, it was actually a better ASIC efficiency. So once you do the parsing within the ASIC, being able to have less information to store in the metadata within the ASIC was actually beneficial. And it allowed us to do actually a stateless proxy mechanism within the ASIC with NoviFlow, NoviFlow's help, which is actually quite interesting in our case because it removes a lot of the complexities and helps us to increase the scale of services we can actually handle. And the proxy function is able to work in both modes, so which was actually beneficial in that case. It also supports us to be able to get ready for a massive scale of instructions, although we do not see them, but it's actually something which enables us in that frame set. Next slide, please. Jesper, can you switch the slide?
Yep, I'm trying. Let's see. what I do?
Okay.
Oh, there you go.
So why do we do? Okay, so why do we do this? Is actually it's a simple service extension, and I want to focus on the simple because we've been trying this for a while, and deployed network service composition in a network is not that trivial. It's still complex. Industry-wide, we all know this. I think I'm not going to make it learned by anybody in the industry. It's a lot of network plumbing complexity, and if it works, you try not to touch it. So we need to figure out the traffic selection criteria, the topology dependencies in that case. Sometimes there's transport dependence. Some functions work only on one type of encapsulation or the other, or they cannot actually be flexible in where you want to be deployed this. And we do what I call a MacGyver-esque networking trick. So we play with TOS, we do PBR, we do route leaks, we create an EVPN sprawl in our networks to try and attach those services together. But beyond connecting those services, a service is actually something more complex as well. So you need, as Jesper explained, the guaranteed service ordering. Sometimes you need a function to work before the other, and vice versa would not work. You need service scalability. It's not because I connect a service to a proxy that actually it scales. Can I actually grow my service? Can I live across a failure? How do I make sure that if it's congested or there's a problem with it, I can actually swap traffic? So the proxy is not just switch from an encapsulation to a function. There's other logic that needs to happen. It's also multi-vendor. So the functions, as Jesper explained, they might not need to be SRv6 aware, but there will. I'm not guaranteed that everything will be a single vendor. And at the same time, how do I support multi-access services? And this is just basic network composition that we have to deal with. And I won't talk when you go into the SD1 realm where it's actually right now even worse. Every SD1 flavor has their own ways of doing service composition. So that was the thought process behind what we did. And also the fact that almost all operators have living assets of network we deployed. We invested into hardware appliances or physical virtual appliances. That's not because we want to move to something, a new network or a new type of encapsulation that we're going to completely rip and replace. So being able to have the flexibility of a proxy, which is not cloud oriented, but can also live with metal hardware and appliances and be able to reuse them was kind of key in our approach. That was why we started with the hardware implementation with NoviFlow. Next slide, please. So basically, what we are able to do is we do dynamic service insertion from the network and be able to redirect traffic to a proxy, and the proxy will be able to do the stateless environment for both physical, virtual, or even containerized with the right plumbing. We do this right now through SRTE. Explicit path traffic engineering, using a route coloring, but the beauty of this is any kind of control plane can be working. I could try some kind of SDN control, I can do PCE, I can do route coloring, and actually if you go farther down the road, you might end up with some kind of service mesh control plane to be able to do this. What we are able to do as well is we do a service proxy we do the new model, the end.sc function. It's actually one SID per service and not necessarily one SID per function, meaning that a service could actually be a single function, but a service could also be multiple functions chained together, which is actually it's an interesting part because beyond use of USID, to simplify the way we do the encapsulation and be able to scale and be stateless, we are able to aggregate some of those functions together and make them look like a service rather than doing the in and outs and recirculation efforts or things like this within the network. And as I explained, it can be done for both for physical, virtual, and cloud-native functions, or CNFs, using the standard SRv model right now, but once it can evolve to other things. The way the service proxy performs its work, it's doing PSP after the traffic is sent to him, and then based on the actual path it had, it just forwards to the next segment routing node. So I can actually create flows for different functions within the same proxy, and based on the information, the original SID list, it's able to reconstruct the destination SID list. I do not need to do a remapping or reparsing. It's just it's kind of seamless within the hardware, which was quite interesting for us. Next slide, please. I call this the perfect storm in the making because our realization is three key components were there to make this successful and actually go at where we are now. The first one was really the SRv6 architecture and network programming. So we created actually a new function with NoviFlow. It's not in a draft. It's not at IETF. It still follows the same SRv6 architecture, and it works. So that proved out that the architecture of the protocol was quite good. So it was actually flexible for us. It's massive scale, and it's also able to be running in various targets. So we're able to run it in programmable ASICs, not necessarily like a memory or resource savvy, but that can also be done in either platform. We just decided to use our MVP with the Tafino platform. And because of the use of V6, we can actually look forward towards scaling those services over our entire network in a seamless fashion. The second key success was mapping a programmable data plane or programmable language for the ASIC with the programmable protocol, I would say. So it was really easy to create new behaviors from concept to line rate hardware in a really fast pace. Because of the logic of the way we can actually program the hardware as it is, it was easy to quickly create fixed recodes. So we did a lot of work with the NoviFlow team, even in kind of a first office application, to fix the pipeline to make sure it was production ready, and it actually worked quite well. And it was also the good thing also, which I like, is because it's innovative in its way and necessarily doesn't need to be coming from the big guys, which is one of the good things from the P4 committee is some of those crazy ideas come and they're not necessarily coming with the same source of thoughts, but we are now able to implement them quicker, which is actually something which is really great. And it's also a great partner ecosystem. In our case was NoviFlow. In the back, we had a lot of work, a lot of collaboration as well from Cisco because we did the integration with them. So it's a deep knowledge of programmable network technology. So with NoviFlow, it was from a crazy idea of prototype in a lab to make it production grade. It was actually something that was doable with them. It was bold and willing to adapt to product from customer use case. So we really sent them out of their comfort zone with that product for that project. But they followed, sometimes sweating, but they kept on going, and it ended up being really useful and really successful in our case. And Actual is a proof in the pudding. Actually, from SRv6 programming, switching from base SIDs to USID into a production code within a week is something quite interesting to see going, and it was actually quite pleasant to see as well. So those three key elements, a programmable protocol, a programmable hardware, and a flexible partner was actually a good road towards our journey towards that success. Thank you very much.